Yeah, you can start.
Okay. Are you seeing everything? Is
Yeah.
it okay? Okay. So, good morning again. Today I'll speak about cycles on algebraic varieties, more specifically on some kind of Fermat variety, a generalized Fermat variety. Okay. So, the idea in this lecture is to speak about exercise 4.2 of Hossein's book on Hodge theory, with emphasis on multiple integrals. So it's the other book, not the one we are following in this course. But I mean, everything is on his page, so you can give a look. So the idea is to give a feeling of how the homology of a Fermat variety look like, and to make some computations. So as in this course, our goal is to choose to speak in a more to focus on a more computational aspects of Hodge theory. It's important that we can explicitly compute the homology groups. So this is what we are going to do, and we are going to get explicit cycles in our group to understand what's happening. So our object is just this affine variety here. So if the m's were all equal, we would have a Fermat variety, but we are considering different m's, so we call this generalized Fermat variety, right? So, I mean, this is our object, and we are going to see how we can look at its homology. Okay, so we can consider this set of indexes, so 0 to mi minus 2, and primitive roots of unity. Okay, and then, so considering these indexes, and here, and the primitive roots of unity, we can define these simplexes here. So for each beta and A, so A is like a string of zeros and ones, and then we can define this delta B beta plus A just as this T1, T2, Tn plus 1 to this 1 over M1, 1 over M2, etc., times our primitive a root of unity. So when it's easy to see that this is actually mu, right? Because when you take this first coordinate and make this to the power M1, we get exactly T1, then T2, or Tn plus 1, and of course the sum of all of them will be 1. So this is our simplices we are going to use.
So it is zeta m1, zeta m2, zeta n plus 1. So you have forgotten the sub-indexes.
Oh, yeah, sorry, yeah. These zetas have indexes also. Yeah, right. Sorry. Yeah, exactly. Yeah. So thank you. So yeah, okay. And then after defining the simplices, we can define for each beta chain, which is just the sum of delta beta plus A, and with a sign which is determined by this sum here. What is this actually? This is just the number of zeros in the string A, right? Because for each, if A is 1, we don't sum anything, but if A is 0, we sum. So we are just counting the number of zeros. And this will determine the sign of our chain in of delta beta in our chain, right? So we have these delta betas, and we will prove that this is actually del delta beta is 0. So we are going to prove that delta beta actually induces an element in the nth homology, and also that delta beta is supported on a sphere. That means that the image of all these delta betas here, the union of the images are, the union is exactly a sphere. So we can actually, in some sense, compute. So what happens is that for any I, I mean, del delta beta is this sum. Sorry, I forgot the sign here again. Here we have a sign -1 to the I, right? And this del I is exactly the restriction of delta beta to the if ith phase of our standard simplex, right? So there is a sign here, sorry. And what happened is that when we restrict to a phase, we are actually considering 0 in one coordinate. So if we change in this coordinate, if we change A to A prime by summing 1 in the ith coordinate, as we are putting 0 on that coordinate, it won't change, but the sign will change, because when we define delta beta, the sign depended just on A, right? So this simplex won't change because we are changing a coordinate which is 0, because t is 0, ti, but we will change the sign. So as we have two options, like 1 and 0, everything will cancel. So let's see the example in the case n equals 1, just to understand what happens. So for delta beta, for n equals 1, we have delta beta is beta plus 0, 0, beta plus 1, 0, beta plus 0, beta plus 1, 1. So if we compute the boundary, we will get this applied to 0, 1, and this applied to 1, 0. And then, okay. And then what happens here is that this will be 0 here and T2 here. And then this will cancel with this will cancel with this, because they have different signs, right? And the same will happen here, okay? Right. So this proves that these delta betas are a cycle, they are in the kernel of del. Okay, so let us consider case n equals 1 again in this to prove they are supported on a sphere, just to understand what's happening, and then we can easily generalize the argument, right? So first we look at this delta beta plus A as a map to C2. So we are looking at the two coordinates here. And on each coordinate, we have a path joining the origin and a root of unity, right? Because this is our coordinate, right? This joins 0 to the root of unity when t varies between 0 and 1. And then in the other line, in the other coordinate, we have the same thing, but on a different direction because T2 is 1 minus T1, right? So if these are going from 0 to the root of unity, then in the other coordinate, we are going from the root of unity to 0, right? Because T2 is 1 minus T1, so when T1 is 0, this is 1, and when this is 1, this is 0, right? So we have one going from the origin to the boundary and the other from the boundary to the origin. And then actually in C2, we have a path from 0 root of unity to root of unity 0, right? Because we start here and go to here and here, okay? And if we do this for our 4 delta betas, right, we are going to get kind of a square this way, which is homeomorphic to S1. It's important to, because, I mean, if you look at these points, here, of course, I mean, these roots are different, but it's okay. But everything will glue in the end. And it's important to say that this is singular, right? This is not a smooth sphere. So sometimes this is important. I mean, that this sphere is not smooth because we have to glue this, and this usually does not glue smoothly. So okay, and obviously this generalized to higher dimensions. So because we can these paths, instead of 4 paths, we would have 8 paths, and then a 2 sphere divided in 8 parts, and then we can glue. And if we have dimension 3, then we would have like 16 and etc. Right? So, and then we can always divide into to the n parts and glue everything like. Okay, so this argument is the same. Okay, so now we are going to give an example of why these cycles are important, right? And we are going to try to explain well why they are important. So we are going to consider a cycle, an element in U, like a subvariety, which is just like the real part of our U. So it's this equation, but on Rn. And we are considering the mi's even because we need this to be a cycle, and we are going to see why. So first, you want to see that this is a cycle. So if this is even, we have that this curve have this form like this, some kind of a more flat circle, and we are going to show that it can be written as a combination of the delta betas. So first, we write this delta as a sum of singular simplexes. So we first consider this. We just isolate y. And then, of course, if we put t to the 1 over m1 here, we are going to get exactly y to be 1 minus t over 1 of m2. And then we can just consider the sign changes we have on both coordinates. So what we get is exactly this. So we are dividing this cycle in 4 small simplexes, right? So joining 1 and 1, and then 1 minus 1, minus 1, minus 1, and minus 1, 1. Okay? So this is our division. So we are writing delta as a sum of simplexes. singular simplices. And then the important thing here is that those sigma 1, sigma 2, sigma 3, and sigma 4 are exactly deltas. So why? So sigma 1 is joining 0, 1, 0, 1, and 1, 0, right? So if we consider the exponent of the root of unit as being 0, as in delta and beta equals 0, 0, we are going to exactly be joining 0, 1, and 1, 0. And then if we consider the exponent to be m2 over 2, we can do this because m2 is even. We are going to get exactly minus 1, because we are going to get the root, like the half root. When we are considering even exponents, minus 1 is of course a root of unity also, right? I mean, because if we take a root of unity and consider the exponent to be m2 over 2, we are going to get 1 to the half, which is actually minus 1. If we see, like, if we do this squared is 1, and I mean, okay, I think it's clear that this is minus 1, and here minus 1, and here minus 1, 0, right? So these are exactly these cycles. And then if we just complete the cycles qm1 over 2, we get exactly this delta, because the other simplices will cancel. Because if we consider like delta beta with beta between 0, 0 and m1 over 2, m2 over 2, what happens is that these delta betas, the big deltas, will appear more than one time, because they appear on delta beta, but they also appear on delta beta plus 1, 0, and plus 1, 1, these things. And then, but the signs will be different, because in some cases you will need A to sum here, and the others no. So they will cancel, right? So, I mean, this is a small computation. I won't do it here because it's a bit big, and I don't want to spend too much time. But it's simple, right? You just need to write the cycles. You take any beta between 0, 0 and m1 and m2, and see how many times each delta beta big appear, right? And then you will see that they will cancel. Right, okay. And in higher dimensions, this was in dimension 1, but in higher dimensions we can do the same. We can look at we can divide this delta in, instead of 4 parts, 8 parts, considering the octants in R3, for example, or in 16 parts, etc., in higher dimensions, and do the same. The important thing in higher dimensions is that a sign will appear here, because if the dimension of the space of our Rn here, so here the dimension is 2, the next one will be 3, the orientation induced here will change, and then we'll have to get a sign here to correct this problem. Okay, so that is the general formula for delta. And actually what we did here is to express a cycle as a combination of our delta betas. And this is actually general. These delta betas will form a basis for the whole Hn. So any cycle can be written as a linear combination of delta betas. And so these delta betas can be used to compute on Fermat variety. So for example, we know that if we consider this Hn, and if we look, this is like an affine chart. If we look at the projective variety, these delta betas can be included there. And as this projective variety is compact, we can always consider a bilinear form on this Hn, right? And then these delta betas are important because we can write the form with a matrix using these delta betas, and we can also explicitly compute cycles here by writing terms of the delta betas. And these delta betas are simple, right? They are not really complicated objects. So it seemed to be a nice way to explicitly compute things in Fermat varieties. And just to finish, it's important to say that those delta betas we are studying here were introduced by Fun, F-Fun in this article. And I mean, in our course, we are going to dive into computational aspects, and so probably these cycles will appear again soon. And here, I mean, the references, so the exercise 4.2 was taken out of this book. Also, Algebraic Topology by Hatcher was used to consider some concepts. And this article by Pham, who first introduced these delta betas. So,
okay,
I think it's this.